All right, now let's talk a little bit about this. This is part B, and it's actually way easier anyway, knowing what we know. Now, when you're looking at something like this isn't going to take that much time. Consider a quadratic equation with integer coefficients and two distinct zeros. If one zero is irrational, which statement is true about the other zero? All right. So, when we look at these, we have 0 is equal to ax minus b, and cx minus d. So this is just your generic form of that, and we know that this is an integer, so it's rational. We know that this whole thing, well, this x right here is irrational. So when this is 0, this won't be 0. If we know that this x is irrational, because it says it, if one zero is irrational, which statement is true about the other zero? Now, I've just chosen this first one to be that irrational solution. You could have chosen whatever, it doesn't really matter. But my main thing is that whatever this is, that 0, I want to point out that it doesn't matter what this turns into. Irrational or rational, it doesn't matter. 0 times an irrational number is 0. 0 times a rational number is 0. Those are your only two options. So it turns out it doesn't matter if this thing ends up becoming rational or irrational. It doesn't matter if this part of it is rational or irrational. At the end of the day, this is going to end up being 0. And 0 times a rational number is 0. 0 times an irrational number is 0. So the answer is C. Because it could happen in both instances. Because again, going back to what we originally had, if x is rational, and we multiply by an integer which is rational, then we get something that's rational right here. The only, no matter what ends up happening here, if this one right here, if this d right here ends up becoming, is irrational, then this whole thing is irrational. But the problem is with that, is that if you take a rational number minus an irrational number, then you will get an irrational number which can't be 0. 0 is defined as rational. Remember from this previous thing right here, you cannot add or subtract something. You cannot subtract an irrational number from a rational number and get a rational number. No matter what happens, if you ever add or subtract an irrational number, it will remain irrational. So this could not have happened and it have been 0. So that's not a possibility. So if your 0 is rational, then this whole thing must have been rational. But it works. You could totally put a rational number in for x, multiply by an integer, it would be rational, and then subtract some rational number, and it would stay, and it would become 0. That would work. You can find something. In fact, let me do it. Cx minus d equals 0. If x, imagine a circumstance where no matter what the letters are, x is d over c. If I plug that in right there, and I say that d is rational, c is an integer, so it is rational, so this is a rational number, just to show you that. Now, if I plug that in, c times d over c, just leaving everything else the same. Cancel my c's because c times d over c, the denominator cancels with the thing you're multiplying by, the numerator, the other fraction, really. And you get d minus d equals 0. 0 equals 0. That is true. So that would have worked. Now imagine a circumstance where where x is an irrational number. Same thing, we're going to end up using x. No matter what happens, this works. X equals d over c. This is rational, which means that the only thing that's making it irrational is that. So if this were true, this is an irrational number. If you were to plug it in to cx minus d equals 0, c times d over c, c would cancel, you get d minus d. It doesn't matter if the first thing is irrational, because the second thing is the exact same number right there. As long as d is the same thing right there, it would equal 0. So your answer ends up being C, because of the fact that at the end of the day, you're going to end up getting 0 right there. You can take an irrational number and subtract itself and still get 0. It's the only way that it works right there. I want you to notice that this thing right here does say a non-zero rational number when they were talking about that. So they even put that in there right there. So let's talk a little bit about this. So a question like this: the figure shows a graph of the function f of x in the coordinate plane. So you have some sort of upside down parabola looking thing. You have a second function, g, which is defined as g of x is equal to negative 3x plus 2. So basically a linear function with a negative slope. Select the correct phrase in each drop-down menu to complete the sentence. So there's usually a little box right here. I don't know why it didn't show up, but either way, I'll draw a little box for y'all. It's fine. And I'll copy it and put it right here too. Okay, so that little box is right there, and we're gonna figure out how to compare these. So select the correct phrase in each drop-down menu to complete the sentence. We're saying f of 2 is less than, or is greater than, or is equal to g of 2. So these right here are going together, and these right here are going together. We're just trying to figure out what symbol or what words we need to put right there, and that is a true statement. So my advice would be to try to graph this function and see what it equals. So let's see. We could do it two different ways. We could either graph this and look at it. So g of x is equal to this. So I'm going to graph my y-intercept. When x is 0, y is 2. When x is 0, this term goes away because it's negative 3 times 0. And then we can use our slope, which is negative 3, which can be written as negative 3 over 1. So our rise is negative 3 and our run is 1, or our rise is 3 and our run is negative 1, using the same stuff that I talked about in the last video. So that means that we go down 3, right 1, down 3, right 1. And we just keep going like that. Or we could have gone up 3, left 1, up 3, left 1. And keep doing that. And then connect our dots. Now you could graph it and like literally just look at it and analyze it from the graph. So f of 2, remember the f function is in black. So f of 2 is right here. F of 2 is right there. Notice that is far above our g of 2. Our g of 2 is down right here. That's far above in the y direction. So in this case, f of 2 is for sure greater than g of 2. That's one way to get your answer. Now let's look at the other one just in case before we talk about a different way to get the answer. F of negative 2. F of negative 2. So that we're going to compare to g of negative 2. So f of negative 2. When x equals negative 2, we're looking right here on our f function. So when x is negative 2, f of negative 2 seems to be 0. Now g of negative 2, that's my red function. That's all the way up here. So it looks like f of negative 2 is less than g of negative 2. It's really, you could graph them and just look at them. Is that part of it above or is that part of it below? So that's one way to do it. But let's try a different way. Let's just plug in the numbers right here and see if that's true. So g of negative 2, g of 2, let's do the first one first. G of 2 is equal to negative 3 times 2 plus 2. So that's equal to, g of 2 is equal to negative 3 times 2 is negative 6 plus 2. So that's negative 4. All right. Oh, I accidentally got rid of my line. But like, imagine you didn't graph it. So g of 2 is negative 4. So we have the point when x equals 2, y equals negative 4. We're really looking for this part right here. And we're going to compare that to our f of 2. So f of 2, we can just look at the graph of that. F of 2 is 8. So g of 2 was equal to negative 4. And f of 2 is equal to 8 from the graph. And when I look at that, it looks like f of 2, which is 8, is greater than g of 2, which is negative 4. That's true. So it gives us the same answer. And you can do that for the f of negative 2 and the g of negative 2 as well. So in that case, we're looking at f of negative 2. Just look at the graph. It's 0. F of negative 2 equals 0. And g of negative 2 is equal to, just plugging it in, negative 3 times negative 2 plus 2 is, negative 3 times negative 2 is positive 6. So it's 14. G of negative 2 is 14. 14 is definitely greater than 0. So when we're looking at comparing these things, we have f of negative 2, which is 0, is for sure less than g of negative 2, which is 14. So yeah, still the same answer. Now this one's a lot easier. Again, little boxes that didn't show up in my PDF for whatever reason. Well, that box is just going to look like that. The cost to manufacture X pairs of sunglasses can be represented by a function C of X. Select the drop-down menus to correctly complete the statement about the function C. So C of 4, which is our output, which is our cost, that is dependent. So right here it says our cost is a function dependent on our sunglasses. Okay? So X is representing our number of sunglasses. So if I look at this and I say 4, that's 4 sunglasses. So when I look at 4 blank pairs of sunglasses, when I look at then blank pairs of sunglasses, well, the only thing that could go in there is 4, because X is representing our pairs of sunglasses, and that is the argument of our function. That's our input. That is what our cost is dependent on. So this right here is like that. A lot of times, I think this question's here to get students to overthink things. But really, if you don't understand anything about function notation, that's where you would goof on this one. Because all the information is right here. This is literally like a little sentence. It's like our cost, C, our cost is dependent on this part, our pairs of sunglasses. So it's all written right there. I got this from my argument of my function because it said how many sunglasses, and sunglasses are X. And that's equal to 398. Well, our cost is 398. So that's right there. It says it right here. Our cost blank. C, the C function, the whole thing, is our output. That is going to tell you exactly what to plug in right there. So all the information's right here. On a question like this, read it carefully, but if it says X is your pairs of sunglasses, that's your input variable of your cost. And it's going to be 4 when it's written right here. All that information is right in front of you. It's super easy to overthink this one, but this one is a gimme problem if you understand your function notation and what it means. Now this one right here, I'm going to do this one and then stop the video. A circular pool of water is shrinking as it drains. The diagram shows the shrinkage. The formula for area, the area A of the circular pool is given by the equation A is equal to pi times r minus 3 all squared, which is the formula for r. Now, all of this is great. This is all great information, but you don't even really need a diagram. You don't even really need a real-life circumstance. All they're really asking here is, hey, solve that equation for r. That's it. That's all they're asking you to do. It doesn't really matter what this thing's representing. It doesn't matter if it's a circle or anything like that. They could have given you a random equation. They're really just saying solve a literal equation for a different variable. So this is an example of literal equations, which are equations that have more than one variable and they never get just numbers plugged in. So we're really just, we have it solved for A right now, and we want to solve for R. But it is nice to know this. Like they actually got the R minus 3 because they're trying to find this radius right here. And we know that this whole thing is R. And if we subtract off this little chunk right here, that's 3. This part right here is just r minus 3. And the area for a circle is pi times the radius squared. But in this case, the radius of this internal part, if you remember from a little bit of that 8th grade geometry, that is r minus 3 squared. But again, we don't really even need to know that part. That's just how they got that function right there. So when we look at this, let's go ahead and just solve it without looking at our options right now. So we have this stuff. Let me just do it like that. I want to solve for r because that's what it says. It says, what is the formula for r? Well, we're going to take this and we're going to solve it for r. Now, the first thing I want to do is I kind of want to get rid of that pi. So I'm going to divide both sides by pi. So a over pi equals r minus 3 all squared. Now, honestly, looking at my answers right here, they all have a pi in a denominator, so that's not helpful. We can't stop there and eliminate anything. Now, last thing I really need to do is I need to take the square root of both sides to get rid of this square. That's how you get rid of a square. It's the inverse function of the square. So I get square root of a over pi. All of that has to be inside of it. Nothing's going to jump out of it. We took the square root of the whole thing. And on the right side, we get the square root of r minus 3 squared. So the square root cancels with the square, and we're just left with r minus 3. Now, to be fair, there is a little invisible plus or minus, but do you see a plus or minus over here? I don't. So they're looking for just the principal square root. Now, honestly, we could stop a little bit right here and at least get rid of 2 of our options. Notice both the a and the pi are inside of the radical, and on this one, it's not. So at least we can get rid of one option. Also notice our 3 is not inside of a radical. Subtracting or adding it from a radical is not going to put it inside of there. So really, anything that has 3 inside of a radical is also needing to go away. Now, honestly, in this case right here, discounting solutions is not even necessary. I would just finish by adding 3 to both sides, and you get square root of a over pi plus 3 equals r. That was, again, me just undoing this negative 3 on the right side because I'm trying to solve for r. I get r is equal to that stuff. So it's got to be this one. But really, all they want you to do on these things is just do the exact same thing and solve for r. So undo your operations the same way you would do if it was just numbers. It's just that you're not able to combine them as you go. It's just, kind of make them concrete. It's just numbers. Oh, I'm going to need to pull up a graph feature for this one.